So, in this session we will take one more derivative based algorithm, which is much more sophisticated than the previous algorithm, that is called the Pan-Tompkin algorithm. This Pan-Tompkin algorithm, it is actually that proposed by Pan and Tompkin, these two scientists, and it is actually proposed for the real time operation, and again it is actually proposed based on the slope, amplitude and width of QRS complex. Okay. So, these are the things keeping in mind that this technique was proposed, and the first part of it is that there is a band pass filter, okay, to clean the signal. We know that when we are using that differentiator or the derivative, so that it will accentuate the high frequency noise. So, we need to get rid of them. So, so first it is passed through a band pass filter, next that differentiator. After the differentiator there is a squaring operation, and we know that if we take the square and if the amplitude is more than 1, actually it gives a non-linear enhancement to the signal magnitude, and the high amplitude one it will be magnified, and the difference between the low amplitude and the high amplitude the signals, they will get separated. That is followed by again a MA filter, because we have seen in the previous two cases that many times the output is jagged. So, to smooth it out, and then the last part is the QRS peaks, and for finding out the peaks, that the Pan-Tompkin has suggested an elaborate procedure for that. And if we look at this part, that is that band pass filter to MA integrated, it would look like that it is just an extension of the previous techniques, but the real actually that that impact comes that in terms of knowledge as well as that the sophistication, that comes in the QRS peak search. So, let us go through that algorithm step by step. So, first this signal is passed through that we have to pass through a band pass filter. For that a low pass filter is taken. That low pass filter the transfer function is given here, and the corresponding that the difference equation is also given, and we have told that one thing, that we have a real time actually that algorithm we are looking for that the Pan-Tompkin has proposed, and for that purpose what they have taken? They have taken a actually IIR filter. They are using that both the poles and zeros, and for the IIR filter, if you look at the weights, all these weights they are actually power of 2. Okay. Either that power of 2, this k is positive or it is negative. So, when it is say 1 by 32, so that means that in that case it is that 2 to the power minus say that 2 to the power 3 is 8. So, 2 to the power 4 is 16, 2 to the power 5 is 32. So, that is 2 to the power minus 5 will give us 1 by 32. So, and that would be implemented by actually 5 right shift operation of the resistor. Okay. So, keeping that in mind, that while we are multiplying with power of 2, that for example, here we are multiplying with that would be left shift operation. One left shift operation will give us multiplication with 2. Here also we will do the same thing, and when we are taking that division by 32, that would be affected by that 5 right shift operations. Okay. So, that is the way that they have implemented, so that the operations can be done in a very fast and frugal manner. That what they have taken, that they have taken the signal that is sampled at 200 hertz sampling frequency, and for that this filter has a cutoff frequency of 11 hertz. So, what we get, that it has a very, I would say that low cutoff, that means the maximum part of the signal and the noise, of course, the high frequency anything above 11 hertz, that will get eliminated. Okay. And that also take care of the power frequency that hum. In North America, that would be 60 hertz, in our country or some part of the Europe, that will be 50 hertz, that is well above this cutoff frequency. So, that will be eliminated by this filter itself. And they have used actually this integer filter for the real time operation. Attenuation at 60 hertz would be more than 35 dB, and that is why that this separation is good enough, and we do not need any more notch filter in this case. Now, that as we told that we take actually that a band pass filter. So, we have to have a high pass filter also along with a low pass filter to do the job, and for that first we start with a low pass filter. Okay. So, this is the low pass filter, the corresponding the difference equation is given. Again you note that all the coefficients are 1. So, no multiplication is required, only addition is required for that, and from that low pass filter, that A corresponding that high the corresponding high pass filter is actually derived from this low pass filter. Okay. And this is the corresponding high pass filter, the corresponding the difference equation also is given, and here that the only term other than that 1, that is 1 by 32, we know that this means that it is power of 2 to the power minus 5, and we can actually incorporate that for 5 right shifts operation. Okay. So, again this high pass filter is also a real time integer filter, and with that we can actually, as we apply it after the low pass filter, this high pass filter along with the low pass filter gives rise to a band pass filter. Okay. And that for this, if we look at that cutoff frequency, the cutoff frequency is low, that is 5 hertz. So, now the signal is actually restricted in between 5 hertz to 11 hertz, only that part of the signal is preserved. So, below the 5 hertz means that all the low frequency signals are also eliminated, and that means Pan-Tomkin has found that most of the energy of the QRS complex is concentrated within this band 5 to 11 hertz, and if we just keep that and throw away the other part, that is good enough for the QRS complex detection. And this real time algorithm that helps us to actually do the fast operation, and for that the integer filter is used again. Now, let us look at the corresponding the difference operator, that for the Pan-Tompkins algorithm, they have a little more elaborate that difference operator, that the difference operator is a weighted actually difference operator is taken. Some of the weights are 2, some of them they are 1, and for averaging that 1/8 is taken. And again you note that this is an integer filter, because the coefficients are integer and the divisions are also power of 2. So, again that multiplication can be replaced by that shift operations here, and after that differentiator that will do the squaring. Now, for in this case that this difference operator, the way it is chosen, it acts as a actually ideal that derivative filter up to 30 hertz. That means, within that band, that 5 hertz to 11 hertz where the signal is present or preserved, at that part it has a linear actually that operation. Okay. And for that when we pass it through that we will get that the high frequency terms will be that emphasized and followed by that squaring operation, which will help us to make it positive and emphasize the large derivatives. And following to the squaring operation, there would be an integration block, which will help in smoothing, and multiple peaks it will actually merge into a single peak. Okay. And for that purpose, that MA filter is used, and they found that n equal to 32, that gives actually good result for Fs equal to 20 hertz. Now, if you ask that why they have chosen n equal to 30, it is difficult to answer. The only way we can think of that they empirically come across this number. If we think in terms of that integer filter, we should have chosen 32 instead of 30. But I think what they may have done, that MA filter, that when you are actually supposed to compute the average, actually they may have taken just the sum, because following these there will be a threshold operation. So, that division by 30, if it is omitted, instead of average we will get the sum, that will simply give a scaling. And so long that our computer that register bandwidth, that it can actually handle that number, there is no problem with that scaling. Okay. That may be that the reason that they have settled it to 30, not gone for 32. So, now here let us look at that how the signal changes by these operations. That first we show at the top that this is the ECG signal, and after the band pass filter we see that the signal is actually distorted, that we get the QRS complex, that is the most prominent one. Also the T signal is also there, it is not completely eliminated. And another thing we note, that if we look at that the position of the R, because of this filtering it has added some delay. Okay. So, the position of that QRS complex or that R wave, that is it has actually that it has been delayed, and the delay is corresponding to that the delay introduced by this band pass filter. Okay. Next, we look at that squaring operation. After the squaring, we get that the output of this T wave that is giving rise to small waveform, whereas QRS complex it is giving a much larger waveform. Okay. So, using that we actually we get that suppression of the other waves and amplification of the QRS complex. So, once it is squared, now we can get that effect that the R wave that gives multiple peaks and that is much higher than the peaks created by the T wave. And you see that P wave hardly that is visible, nothing is there almost. Okay. And once it is passed through that integrator, that is the MA filter of order 30, then we get that it becomes a solid actually stump, that all the peaks they get merged and gives rise to a post kind of structure here, which can be actually thresholded to find out that there is a QRS complex is present at this position and it is very difficult to miss. Okay. So, up to this we get actually from the knowledge of the previous algorithms. Now comes the special contribution of Pan-Tompkin, that the first change they have made, they made the thresholding should be adaptive. Okay. That is the beauty of the Pan-Tompkins algorithm. So, for that what they have done, that they have introduced couple of terms, that first one is SPK1, second is NPK1, okay, and two threshold 1 and threshold 2 they are introduced. Okay. Out of that if we look at that here the inputs are the peak. Peak means that the overall the peak, whenever after we take a threshold, that the peak what we get, that we get anything above that threshold, that is a peak. So, using that we are actually updating that SPK1, that is the signal peak running estimate, and NPK1 is a running estimate of the noise peak. Okay. So, if we take a threshold, whatever we get above the threshold, that will could be a signal peak or a noise peak. If it is a signal peak, that is used to update the running estimate of the signal peak. If it is a noise peak, then that peak is used to update the estimate of the noise peak, and in both the cases what we get, that we are taking actually 0.125 this fraction, this comes out of 1/8. Okay. Again it is a power of 2 to the power minus 3 has been taken, and this part what we are taking, this is actually if it is 1/8, the other part is 7/8. So, the previous value whatever was there, it is multiplied by 7 and then 3 right shifts will give. So, 1/8 part of that previous estimate that is taken, and it is actually used to modify both the signal peak and the noise peak. Okay. And after that will go for the selection of the threshold, that, and the philosophy is very simple, that threshold should be above the noise peak, so that no noise peak should be detected. So, and it should be much lower than the signal peak, so that we are able to catch actually all the signal peaks. There should not be any miss actually of signal peak. So, what they have proposed that the threshold 1, it should be above the noise peak. So, that is the baseline, and then the difference between the signal peak and the noise peak, that running estimates, the difference of that, 1/4 of that difference is added with the noise peak. So, that would be the threshold. Okay. That is the threshold 1, and 50% of that threshold 1 is taken as the threshold 2. So, that is that number of actually that terms we get, and this is how we define the threshold 1 and threshold 2. Okay. Now, let us go through the definitions once more, so that we can remember them. That we have the peak 1 that is the overall peak. Whenever we get one post that is above the threshold, the peak of it is taken as PK1, peak 1. Then that will have some more steps to find out whether it is a signal peak or a noise peak. If it is a signal peak, then that peak is actually used to again update the signal peak estimate, running estimate. If it is a noise peak, then that is used to update the running estimate of the noise peak. And that we have used that using that these two running estimates of the signal and the noise peak, that the threshold 1, that is the first estimate of the threshold, first threshold, that is actually calculated, and half of the value of the first threshold, that gives a lower threshold, that is we call the second threshold, okay, or threshold 2. So, with that we proceed, and here one more thing, that if a signal or a peak we miss by the threshold 1, that means a time has passed, we could not get any peak above the threshold 1, then we would fall back on the threshold 2 and try to find out whether we can get any peak. And if we get a peak by threshold 2, and if that peak is a signal peak, then our speed of update of the signal peak becomes more. Instead of 1 actually 8th, we take 1/4 part of this new peak and 3/4 part of the previous estimate of the signal peak, and we update that running estimate. That means, what we realize that due to some reason, maybe contact resistance or so, that signal amplitude has reduced, and because of that we could not get any peak above the threshold 1. Under that situation, we need to update the thresholds, so that we do not miss any peak, and for that we have used that second threshold to get that peak. Now, after getting that peak, if it is a signal peak, we should update that estimates more quickly, so that next time such thing does not occur. So, we increase the speed of adaptation in this case. Now, we get the surge back part of it. Okay. Here we have two quantities of the RR average. Okay. If we have a ECG signal, we know that we get the P Q R S T, then a gap, again we get P Q R S T. So, in between the two actually beats, this the difference between the two R's, that is called RR interval. and for this RR interval they are having actually that two average actually estimates of the RR interval. The first one, it is taking the raw one, that whatever the peaks are we get, that we take those that corresponding the RR intervals, and that gives rise to the RR average one. And from these RR intervals, raw RR intervals, we can say that we refine them, and the refined estimate that is taken as RR dashed, that is used to calculate the second average. Now, how that is refined? There is a limit, lower limit and upper limit that is set, that if the RR average 2 is taken as actually a more stable or the robust estimate of the RR interval, if the lower limit is actually set as 92% of it and the upper limit is taken as the 116% of it. Okay. So, please note that they have not taken a symmetric window. If this is 100%, that lower side, if this is 100%, lower side they are taking it 92, that means an allowance of 8, and upper side 8%, upper side they are taking it 116%, means an allowance of 16%. If it is within that, then that RR interval we call as RR dashed, that means that is an acceptable one. If it goes outside that, then what could happen? RR interval, if it is bigger, means bigger than that within this limit, even above the 116%, that means that is an unusual kind of situation. For a healthy person, the person that heart is beating, so that the QRS complex would be there all the time. So, if it is absent, so what is actually concluded here, that our algorithm has missed to peak actually that QRS that beat or the R actually peak. So, that means we have missed one, and that is why RR has become more. The other option could be, if it is very small, that is less than 92% of the RR average, that such a sudden change in the beat does not happen, even if there is change in the rhythm, that is a gradual one. If the RR interval is smaller than that, that signifies there must be a noisy peak that has actually reduced the RR interval. So, now we need to take care of that noisy actually peak. So, if it is below that, then we get that new peak as a noisy peak, and that helps us to actually change that running estimate of the noise peak. And if it is within this interval, then it is a signal peak, then that helps us to find out that from the signal peak that we can get that RR average 2, as well as we can estimate or update the estimate of the signal peak. And if it is above, that means we have missed something. So, we need to look back and find out that missed peak, and that is the part we call as search back operation. So, as a part of it, what is done, whenever the QRS waveform it is not detected within that a certain interval, that is called that RR missed limit, then the QRS peak between the threshold 1 and the threshold 2 is taken. In fact, the first part is imperative, we call it is missed because there is no peak above the threshold 1. Okay. And in that situation we can get a peak only if it is above threshold 2, and that essentially means it has to be between these two threshold, threshold 1 and threshold 2. So, that becomes the new peak what we take here, and that RR missed limit is actually set pretty high. It is taken 116% of the RR average 2. Okay. So, that RR average 2 is the stable average or the robust average of the RR interval. If it is 166% of that, that means 66% more is considered as the limit. If still we do not get that the R peak, that means we are sure that we have missed that R peak, because the signal cannot actually heart can stop beating that long, or the frequency cannot go down that low. So, we should go for that the threshold 2 and take that peak above that threshold. Okay. So, when the heart rate is normal, that we do not have any problem, then we get that RR average 1 and RR average 2, they should be similar. There is no reason that they would be different. However, if there is fluctuation in the heartbeat, then these two can actually vary. And using this algorithm, which is a real time algorithm, the Pan-Tomkin they found that they could achieve a very low error rate, that is 0.68%. Okay. And that means only 33 beats per hour for a huge database of 116,000 beats of 24 hours recording of 48 patients. So, with a very exhaustive set of database of 48 patients, and by collecting their 24 hours recording, that means throughout the day whatever the changes has occurred, they could actually get a very good actually estimate, only 0.68% that the RR the beats R beats are missed in this case. That means less than 1% actually loss. Okay. So, that is the way Pan-Tomkin has contributed in terms of a very sophisticated that QRS detection algorithm. Now, we will go through another small part before concluding this session. We have seen that the cardiovascular system, and a part of it we told that the left ventricle, which is pumping out the blood through the arteries and which reaches throughout the body, that the first the QRS complex signifies the start of the compression, then between S and T that the contraction actually remains, and because of that the blood flows out of the ventricle because of that pressure, and when the T wave comes, which signifies the start of the relaxation of the ventricles, the moment the pressure of the blood inside the left ventricle, it becomes lower than that of actually that means the blood pressure within that aorta. So, then the valves that is helping for the unidirectional flow of the blood in the aorta, that will get closed. Okay. And that gives rise to a small dip in the pressure, okay. And that will remain constant after that, because the valve is closed. Even if the ventricles relaxed, it will not allow for a backflow of the blood. Okay. and that part we would like to capture, okay, and that can be done by the carotid pulse signal. Okay. That we know that the carotid means there is an artery that is going towards the head for supplying of the blood. So, when we have the QRS complex, here is the QRS complex of the ECG, that is associated with some noise called actually S1 signal, and S1 signal we get in the PCG signal, the phonocardiogram. Okay. Phonocardiogram is that audible sound we get near the heart, and how that is generated? It is generated by the sound of the valves, and again that the blood is oozing out from the ventricles to the arteries, or in the left ventricle to the aorta. Now, it gives rise to turbulence, and we get that noise as the S1 signal. Okay. So, S1 signal can actually help us to find out that whether it is the normal sound, or in case of some stenosis in the artery or imperfection in the valve, say at the time when the blood is flowing from the left ventricle to the aorta, if that the valves in between that aorta and the ventricles, they should have closed before that. If they have not closed properly, some blood can actually backflow, and that will give rise to some sound. So, all such things will be actually depicted in the S1 sound or S1 vibration, and that the way we are getting here the PCG signal, it is a very clean one or clean rendering of it. It is actually superimposed with lots of noise, including that power frequency noise and the high frequency noise. So, we do not get such clean signal. So, we need to really have some idea that where the S1 and S2 sounds are occurring. So, the first trigger to get the position of S1 comes from the QRS complex, and already we have seen that how we can capture the QRS complex, the three algorithms we have learned. Now, for the S2 one, that comes when the ventricles relax and the valves which were so far allowing the flow of the blood from the ventricles to the arteries, they closes down. If that valves get calcified, so instead of a soft sound, it will make a metallic sound, and that will give rise to an increase in the S2 sound. However, to get that where that is occurring, it becomes very difficult, because a T signal is a non-event. It's subdued signal. We cannot get actually when actually it is finishing. So, instead of looking at ECG from where you cannot get really the boundary that of the end of T signal, we go for the carotid pulse signal, which picks up after the QRS complex, the pressure is increasing, and when the valve is actually closed, there is a sudden dip which gives rise to a dip in the pressure. Again, as the valve is closed, that pressure remains constant and slowly that is going down. So, we can tell this part of the pressure is the systolic pressure, and this part is the diastolic pressure actually. Okay. So, in between these chains, this notch in the diatric this carotid pulse, if we can catch this position, it can help us to get the location of the S2 signal in the PCG signal. So, that is the importance of the carotid pulse signal and the notch. Okay. These two are very close to each other. So, Lehner and Rangan, they have used again a second derivative of the base technique. So, they have suggested that let us take the second derivative of the carotid pulse signal followed by a MA filter, and this will give rise to two peaks. One peak would be for the actually that if we take the second derivative, that it will give the peak somewhere here, where there is a increase in the signal amplitude, again that will give a peak here. Okay. So, to get that is why they are talking about that we would look for that second peak. Out of the two peaks, the second one is taken, that is corresponding to the diatrice notch. Okay. And diatrice notch may be located that where the peak comes, they look for local minima around that peak, okay, by taking an interval of plus minus 20 millisecond around that second peak. Okay. That is how they could actually get the location of the diatrice notch, and we know from that we can get that time window where the S2 is located. Okay. So, thank you.